Every history book begins with humans, but Earth is 4.5 billion years old. We have been here for a fraction of that time. 56 million years ago, something pumped a massive burst of carbon into the atmosphere. The planet heated up fast. Scientists still argue about what did it, and Webb just proved that rocky planets billions of years old can hold onto their atmospheres long after we thought they'd be destroyed. So here is the question: what if something was here before us? We are going to walk through the rock record, the deep ocean, the oldest crystals on the planet, and what Webb is reading in the atmospheres of worlds far away. If you find this mind-bending, like and subscribe. We are just getting started. Prepare yourself. We begin. 4.5 billion years. That is how old Earth is. To feel what that number means, picture a calendar where one page equals 1 million years. You would need 4,500 pages to reach the beginning of our planet. Human civilization sits on the last half of the very last page. Everything we know about history, the pyramids, the Roman Empire, the first iPhone fits inside a sliver so thin you could barely see it with your eyes. And here is where it gets uncomfortable. For most of those 4,500 pages, something else was in charge. Not humans, not our ancestors. Something else entirely lived on this planet, shaped it, breathed it, and in some cases, nearly destroyed it. We know this because the rocks told us. Scientists drill into the ground and pull out layers of ancient Earth, the way you might flip back through an old notebook. Each layer is a different era. Each era had different rulers. For the first several 100 million years, the ruler was heat. The surface was molten rock. Nothing could survive. Then the planet cooled, and water arrived, and microscopic life showed up in the ocean. Those tiny organisms ran the world for over 2 billion years. They were so successful, they accidentally changed the entire atmosphere. More on that soon. Then came the explosion. Around 540 million years ago, complex life burst into existence like someone turned on a light switch. Shells, eyes, limbs, predators, prey. The ocean filled up with creatures so strange they looked like nightmares. The land came later. Then came the animals. First in the sea, then crawling onto shore, then flying, then huge. Reptiles ruled for over 160 million years. To put that in perspective, the time between us and the dinosaurs is shorter than the time the dinosaurs themselves existed. And then one rock the size of a small city hit the Yucatan Peninsula, and the world reset again. 66 million years of mammals followed. Most of them were small and quiet and forgettable. Then, around 2.5 million years ago, something in one primate lineage shifted. The brain got bigger, the hands got cleverer, and about 300 years ago, that lineage started burning things at an industrial scale. That is us. Page 4,500, the very last few lines. Now ask yourself an honest question. With 4.5 billion years of history behind us, and with extinction events that wiped out almost everything multiple times, how confident can we really be that we are the first ones who ever built something worth noticing? The honest answer is, we are not confident at all. We just never seriously looked. Scientists at the University of Rochester and at NASA's Goddard Institute put this into a formal paper. They called it the Silurian hypothesis. They were clear that they doubted a prior civilization existed, but they also admitted something important. If one had existed millions of years ago, the chances of us finding direct evidence today are extremely small. The geological record does not preserve things forever. It erases them. So, we are left with a question that science is only beginning to take seriously. What if the board was wiped clean before we arrived? And what if the Webb Space Telescope is now giving us the tools to check? That is exactly what we are going to explore. Each chapter of this story goes deeper, weirder, and older. We are going to read the rock, read the sky, and read the evidence that something strange has been happening on this planet for a very long time. What comes next will make you rethink every assumption you have about who got here first. On Christmas Day, 2021, a rocket launched from South America carrying the most powerful space telescope ever built. It took 30 days to reach its destination, a point in space 1 million miles from Earth. Engineers held their breath the entire time. 144 individual failure points. Any one of them could have ended the mission. None did. The James Webb Space Telescope opened like a golden flower and began staring at the universe. What it does is deceptively simple to describe and almost impossible to fully comprehend. It sees in infrared light, heat, the kind of light our eyes cannot detect. And because infrared light travels through dust clouds that block regular visible light, Webb can see straight through walls of gas and debris that blinded every telescope before it. Here is why that matters for our story. When light passes through a planet's atmosphere, different molecules absorb different wavelengths. Carbon dioxide absorbs one, methane absorbs another. Water vapor has its own fingerprint. Webb reads those fingerprints from millions of miles away and tells us exactly what a planet's atmosphere is made of. Think of it like this. You are standing a mile away from someone's house. You cannot see inside, but you can see the smoke coming out of the chimney. And from the color and the smell of that smoke, you can figure out what they are burning. Webb does that with entire planets. Before Webb, we could detect that a planet existed. We could measure its size and its orbit. That was it. We were reading the outside of the envelope without knowing what was inside. Webb opened the envelope, and immediately it started finding things nobody expected. Galaxies that were too big and too bright and too developed for how early they appeared in the universe. Carbon clouds forming earlier than any model predicted, pushing back the clock on when life could have first been possible in the cosmos by billions of years. Atmospheres on planets that should not have been able to hold an atmosphere. Chemicals in the air of worlds light years away that, on Earth, are only made by living things. Each one of these discoveries landed like a small earthquake in the scientific community. But the one that connects most directly to our story came from two different directions at once. First, Webb looked at a scorching ancient world called TOI 561b, twice as massive as Earth, and orbiting a star twice as old as our Sunday. And it found something that should not have been there. Second, Webb looked at a distant ocean world and found chemical signatures that, on Earth, only life produces. Both discoveries changed how we think about how long planets can stay active, how long atmospheres can survive, how long a world can remain capable of hosting something. And that changes the math on Earth. If a planet twice Earth's mass can hold onto an atmosphere for 10 billion years through conditions that should have stripped it bare, then Earth at 4.5 billion years is not old. Earth is middle-aged. And the question of what was happening here in its earlier chapters becomes something worth taking very seriously. Webb did not just open a window to distant worlds. It handed us a new way to think about our own. And what it found when it looked at those ancient planets is going to make the rest of this journey far stranger than you are expecting. 560 light years from Earth, a planet is on fire. It orbits so close to its star that a full year passes in 10.5 hours. One side of the planet never turns away from the heat. That side bakes at temperatures that would melt steel in minutes. The other side is in permanent darkness. Scientists called it TOI 561b. It is twice as massive as Earth. Its star is twice as old as our Sun, which makes this system around 10 billion years old. For context, our entire solar system is only 4.5 billion years old. This world has been sitting in that fire for twice as long as Earth has existed. Every model said it should be a bare rock. Actually, not even a rock. A scarred, airless, scoured ball of dense minerals with nothing left on its surface but the aftermath of 10 billion years of punishment. Webb looked at it and found something else entirely. The telescope measured the heat coming off the day side of the planet. A bare rock at that distance from its star should reach about 4,900 degrees Fahrenheit. Instead, Webb read the temperature as roughly 3,200 degrees. Still scorching, but nearly 2,000 degrees cooler than it should be. That gap is enormous, and there is only one explanation that fits: an atmosphere, a thick one. Something is distributing the heat, moving it from the burning day side toward the dark night side, cooling the surface enough that Webb could measure the difference. Scientists ran every other possibility first. Could the lava ocean itself be circulating heat? Partially, yes, but not enough. Could a thin film of rock vapor account for the reading? Also no. The only model that matched the data was a rich blanket of gases, possibly including water vapor, carbon dioxide, and other compounds rising from the churning magma below. This world is a wet lava ball wrapped in its own recycled atmosphere. Here is why this matters beyond just being a wild discovery. For years, scientists believed that small, rocky planets orbiting close to old, active stars could not hold onto their atmospheres. The radiation pressure and stellar winds were just too intense over too much time. That assumption shaped how we thought about what kinds of planets could support long-term chemistry, long-term conditions, long-term anything. TOI 561b tore that assumption apart. If a rocky world twice Earth's mass can maintain an atmosphere for 10 billion years through conditions that violent, then the survival window for planetary chemistry is far longer than we thought. Planets can stay geologically active, atmospherically rich, and chemically complex for enormous stretches of time. Translate that back to Earth. Our planet is only 4.5 billion years old. By the standard TOI 561b just demonstrated, Earth is not even halfway through its potential active lifespan. The chemistry on this world, the conditions that allow for complex things to happen, has been running for billions of years already, with billions more potentially to come. And that raises a question nobody asked loudly enough before Webb turned its mirror on that lava world. If the conditions for complexity can survive this long, what might have used those conditions in the chapters of Earth's story that came before us? The next chapter of Earth's own geological record holds something strange, something that looks a lot like a fingerprint. 56 million years ago, something happened to Earth's atmosphere in a geologically instant period of time, possibly as short as 5,000 years. A massive amount of carbon flooded into the air and ocean. Temperatures across the planet spiked 5 to 7 degrees Celsius. The oceans became more acidic. Thousands of species of tiny marine creatures died off entirely. On land, mammals shrank in body size as their food supply collapsed. Scientists found this event preserved in layers of rock and seafloor sediment all over the world. They called it the Paleocene-Eocene thermal maximum. It lasted about 200,000 years. Then, carbon levels gradually pulled back down, and the planet recovered. Sounds like a known geological event, right? Here is the problem. Scientists still argue about what triggered it. The leading explanation involves massive volcanic activity under the North Atlantic Ocean, where ancient lava fields intruded into organic-rich sediments and cooked them, releasing stored carbon into the atmosphere. There is evidence supporting this. Mercury deposits in sediment cores from North Sea drill sites suggest volcanic pulses right at the boundary. But there are problems with that explanation too. The speed of the carbon injection is hard to account for with volcanism alone. Some estimates suggest the rate of carbon flooding the atmosphere was comparable to what humanity is pumping out today from burning fossil fuels. Volcanism is usually much slower. In 2018, two scientists named Adam Frank and Gavin Schmidt published a paper asking a question that sounds like science fiction but is grounded in geology. They called it the Silurian hypothesis. They asked, if an industrial civilization had existed on Earth millions of years ago and burned through fossil fuels at a rate similar to ours, would we be able to detect it in the rock record? Their answer was deeply unsettling. Mostly no. Chemical traces would survive in some form for tens of millions of years. A spike in carbon isotopes, a brief temperature anomaly, elevated levels of certain metals, but the physical structures, buildings, roads, machines, would be gone in less than 1 million years, completely recycled by the planet. They were clear that they did not believe a prior civilization actually existed. Their paper was a thought experiment, a way of asking whether science even has the tools to check. But here is what sits in the back of your mind once you read that paper. The Paleocene-Eocene thermal event matches, not perfectly, not conclusively, but structurally, a fast carbon spike, a temperature surge, a recovery period. It resembles the kind of fingerprint that an industrial episode might leave behind if enough time had passed to blur the details. Scientists have other explanations. Volcanism, orbital shifts triggering permafrost melt, deep-sea methane hydrates, destabilizing. Any one of these could be the cause. But none of them is fully proven, and the fact that the event is still debated after decades of research means the question has not been answered. Something injected carbon into Earth's atmosphere at a speed comparable to human industry 56 million years ago. We still do not know exactly what. Imagine burying a smartphone in your backyard. Come back in 1 million years and dig. What do you find? Nothing. No glass, no metal casing, no chips. The silicon might leave a faint chemical trace in the soil. The rare earth metals inside might show a slight concentration in one layer of sediment, but the device itself, gone. Now imagine an entire civilization burying itself. Every road, every building, every machine. Come back in 50 million years and look. This is exactly the problem scientists wrestle with when they ask whether a prior civilization could have existed on Earth and left no obvious trace. The geological record is not an archive. It is a demolition site that occasionally saves something by accident. Here is how it actually works. Sediment builds up in layers over time. These layers compress into rock. In the right conditions, bones and shells and sometimes even soft tissue leave impressions in that rock. Fossils form. Scientists read them. But most things do not fossilize. A creature needs to die in the right place at the right time, in sediment that is wet enough to preserve its shape but not so active that it grinds the remains away. The vast majority of organisms that ever lived on Earth left no fossil at all. Now add a second problem: plate tectonics. The seafloor is constantly moving. Plates of ocean crust dive under continental plates in a process called subduction. The seafloor is completely recycled every 200 million years or so. Everything on the bottom of the ocean is eventually swallowed by the mantle and melted. So, any civilization that existed more than 200 million years ago and was primarily ocean-based would have left almost nothing above the geological noise. A land-based civilization lasting only a few hundred years, the same length as our current industrial era, would leave carbon isotope spikes, perhaps some unusual metal concentrations, maybe traces of synthetic compounds in the right sediment layer. Over millions of years, erosion, subduction, and chemical cycling would smear even those signals into something that could easily be mistaken for volcanic activity or orbital changes. The scientists who wrote the Silurian hypothesis calculated that the chances of finding physical artifacts, actual objects, from any civilization older than 4 million years are essentially zero. Brains do not fossilize. Cities do not fossilize. Only rock and bone and shell and carbon leave memories in the record, and only under very specific conditions. This means we are trying to solve a mystery with most of the evidence already gone. Think about what that means for the carbon spike 56 million years ago. If something did cause it, and if that something left traces, those traces would look exactly like a blurred chemical smear in a sediment core. Which is exactly what scientists found. There is no smoking gun. The gun, the hand that held it, and the room it was fired in have all been recycled by the planet. But the bullet is still lodged in the rock, faint, blurred, and still unexplained. And that is only one of the mysteries waiting in Earth's deep past. The next one goes back much farther. Earth formed 4.5 billion years ago. The oldest rocks we have found on Earth's surface are 4.16 billion years old. They come from a remote area of northeastern Canada, called the Nuvuajitu Greenstone Belt. Scientists confirmed this age in 2025. Before this discovery, we had almost nothing from Earth's earliest period. That gap, roughly 300 to 400 million years of missing geological record, has a name. Scientists call it the Hadean Eon, named after the Greek word for the underworld. We know very little about it because almost nothing survived. During the Hadean, the planet was being bombarded by asteroids and comets in an event called the Late Heavy Bombardment. The surface was largely molten. Any rock that formed was blasted apart, melted down, and reformed. The ocean was either boiling or being vaporized and then raining back down as the bombardment continued. The oldest surviving witnesses to this era are not rocks. They are minerals, tiny crystals called zircon, found mostly in Western Australia, have been dated to 4.4 billion years ago, nearly the beginning of Earth's existence. These microscopic crystals are almost indestructible. They survived everything. And inside some of those ancient zircon crystals, scientists found something that stopped them cold: carbon, with a chemical signature suggesting organic origin. Life on Earth may have begun more than 4 billion years ago. That is earlier than almost any model predicted. If correct, it means living chemistry was operating on this planet while the surface was still being pummeled by space rocks. Here is where this connects to our larger question. The Hadean Eon is a black hole in Earth's history. We cannot see into it clearly. We have fragments of minerals and chemical hints, but no coherent picture. If anything complex had existed during the late Hadean or early Archean and been wiped out, we would have almost no way to know. The planet erased itself repeatedly. Impact events, volcanic floods, tectonic churn. Every few 100 million years, something reset the surface. We are not the first complex chemistry on this planet. We might not even be close to the first. The question is how far back the chain of potential owners goes, and how many times the slate was wiped before someone left marks we can still read. The deepest marks are not objects, they are gases. And the most dramatic gas event in Earth's history nearly ended everything before it even really began. Around 2.5 billion years ago, tiny blue-green bacteria living in the ocean figured out how to split water molecules and use sunlight to make food. This was the invention of photosynthesis. And it was, from the perspective of almost every other organism alive at the time, an extinction-level catastrophe. Here is why. Before these bacteria arrived, Earth's atmosphere had almost no oxygen. The early ocean was full of dissolved iron. Most life that existed fed on chemical reactions in the absence of oxygen. The entire biosphere was built around a world with no free oxygen. Then the cyanobacteria started pumping it out. At first, the oxygen was absorbed. The iron in the ocean grabbed it and rusted, creating the red banded iron formations you can see in ancient rock all over the world. Volcanic gases soaked it up. The chemistry of the planet worked overtime, trying to neutralize it. But the bacteria kept going. For hundreds of millions of years, they kept pumping. Eventually, the ocean ran out of iron to absorb the oxygen. The atmosphere ran out of volcanic gas to neutralize it. And around 2.4 billion years ago, free oxygen began building up in the atmosphere for the first time. For organisms that had never evolved to handle oxygen, it was poison. Free oxygen destroys biological molecules. It corrodes. It reacts violently with organic chemistry that was not designed to tolerate it. Scientists call this the Great Oxidation Event. In terms of casualties, it may be the largest extinction event in Earth's entire history, larger even than the asteroid that killed the dinosaurs. Entire kingdoms of life that had ruled the planet for over 1 billion years were wiped out, pushed underground, pushed into oxygen-free pockets of the ocean and sediment where they still live today, hidden from a world they once owned. The organisms that survived were the ones that either could handle oxygen or learned to, and then, slowly, life evolved to use oxygen as fuel. Aerobic respiration, the chemistry that powers every animal alive today, including you. The Great Oxidation Event took over 200 million years to fully unfold. It was a revolution in slow motion, and it completely erased the world that came before it. Any evidence of what lived in those pre-oxygen oceans is sparse and scattered. We have some fossils, we have chemical signatures, but the oxygen revolution chemically transformed the sediments, the water, and the rock, rewriting the record that had been building for over 1 billion years. If a world full of complex chemistry existed in the billion years before oxygen, most of its story is gone. And what came next was even more extreme. 800 million years ago, Earth turned white. Ice spread from the poles toward the equator. Glaciers advanced across continents. The ocean began to freeze at the surface, starting at the edges and creeping inward. Year by year, decade by decade, more of the sea locked up in ice. The planet reached a point where the entire surface, ocean and land alike, was covered in ice and snow. Scientists call this snowball Earth. They believe it happened at least twice. A frozen ocean reflects sunlight back into space instead of absorbing it. This is called the albedo effect. The more ice forms, the more sunlight bounces away. The colder it gets, the more ice forms. A runaway feedback loop that could take millions of years to break. What eventually broke it was volcanic activity. Volcanoes erupting beneath the ice and beneath the sea kept pumping carbon dioxide into the atmosphere, even while the surface was locked solid. Over millions of years, without rain to wash the carbon dioxide out of the sky, it built up until the greenhouse effect finally overwhelmed the ice. The planet thawed suddenly and dramatically. When Snowball Earth ended, the warming was intense. Temperatures swung from extreme cold to extreme heat in what was, geologically speaking, a very short time. Here is why this matters. Snowball Earth episodes happened more than once. Each one lasted tens of millions of years. The glaciers ground across the surface, crushing sediment, erasing formations, redepositing material in entirely different places. Any fine-grained chemical record that might have existed in ocean sediments was physically destroyed by the ice grinding across the seafloor. Any life that could not survive in small pockets of geothermal heat or under ice in liquid water was eliminated. After Snowball Earth ended, the world that emerged was chemically and geographically different from the one that had been buried under the ice. And shortly after the planet thawed, something happened that scientists still find deeply mysterious. Complex multicellular life exploded into existence almost overnight, 540 million years ago. Something switched on. Before this moment, life on Earth had been mostly microscopic for over 3 billion years. Single cells, simple colonies, soft-bodied creatures, leaving only faint impressions in muddy sediment. Then, in a period that, by geological standards, is almost instantaneous, virtually every major body plan for complex animal life appeared simultaneously. Animals with eyes, animals with shells, animals with legs, animals with claws and jaws and fins. The fossil record goes from almost empty to crowded in what may have been as little as 20 million years. Scientists call this the Cambrian explosion. It is one of the most studied and most debated events in all of paleontology. And after more than a century of research, there is still no single agreed explanation for why it happened so fast. Some scientists point to the rise of oxygen. After 2 billion years of building up, oxygen levels in the late Precambrian atmosphere finally reached the threshold needed to power complex metabolisms. Animals with muscles and organs and brains need enormous amounts of energy. Oxygen is how you get it. Others point to the end of Snowball Earth, which thawed nutrients out of deep sediment and flooded the oceans with the chemical building blocks that complex life needed to diversify. Some point to an evolutionary arms race. Once one creature evolved eyes, everything else had to evolve either better eyes or better camouflage to survive. Once one animal evolved a shell, predators evolved harder jaws. The development of one trait cascades into others. But here is the thing that gets overlooked in most explanations. Before the Cambrian explosion, there were already sophisticated organisms. The Ediacaran fauna, creatures that lived in the 50 million years before the explosion, were large, complex, and soft-bodied. And then, most of them vanished. An extinction event wiped them out just before the Cambrian began. Something cleared the way. And then, almost immediately after, the most diverse and rapid biological diversification in Earth's history filled the gap. This pattern, an extinction clearing the stage followed by an explosive diversification of new life, will repeat itself throughout Earth's story. Each time, what comes after looks nothing like what came before. And what came roughly 400 million years after the Cambrian explosion had features that some scientists found deeply unsettling. In the late 1970s, a paleontologist named Dale Russell was studying a small dinosaur from the Cretaceous period. It was called Troodon, about the size of a large dog, bipedal meaning it walked on two legs. It had forward-facing eyes, giving it depth perception, grasping hands, and, relative to its body size, one of the largest brains of any dinosaur known. Russell ran a thought experiment. What if the asteroid had not hit 66 million years ago? Dinosaurs survived another 50 million years. What might Troodon's lineage have become? He built a model. He called it the Dinosauroid. It was bipedal, large-brained, with grasping hands. A humanoid body plan, not because Russell was being dramatic, but because the pressures of intelligence tend to push evolution towards certain practical forms. A brain needs to be close to the sense organs. Hands need to be free for manipulation. Upright posture frees the hands. The science community debated the model for decades. Many experts argued the brain architecture of dinosaurs and birds was too different from mammals to ever reach human-level cognition. Others pointed out that we really do not know how bird brains work at their upper limit. Crows can solve puzzles. African grey parrots can identify objects by name. These are avian dinosaurs, and they got there on a completely different evolutionary path from us. The question of whether a dinosaur lineage could have crossed the threshold into tool use, language, and eventually technology is genuinely open. The ingredients were there. Troodon-type creatures had been evolving for over 100 million years by the time the asteroid hit. That is more time than it took mammals to go from small tree shrew-like creatures to building the internet. And here is the uncomfortable calculation. Dinosaurs as a group ruled this planet for around 160 million years. Our entire evolutionary lineage from the earliest apes to the present is about 6 million years. Our industrial civilization is around 300 years old. If a lineage with Troodon's brain had been given another 50 million years, and if intelligence compounds the way evolution sometimes suggests it does, the math is open-ended. We do not find evidence of a dinosaur civilization. But absence of evidence is not the same as evidence of absence, especially when the geological record can only keep secrets for so long before it destroys them. And what happened to the dinosaurs connects to the deepest reset button Earth has ever hit. Earth has experienced 5 mass extinction events since complex life began 540 million years ago. 5 times the planet came close to starting over. The first was 440 million years ago, at the end of the Ordovician period. A brief but savage ice age collapsed marine ecosystems. Around 85% of species vanished. The second came 365 million years ago, in the Devonian period. The cause is still debated. Ocean oxygen levels crashed. Shallow seas emptied. About 75% of species were lost. The third was the worst. 252 million years ago, at the end of the Permian period, something triggered an event so catastrophic that scientists call it the Great Dying. Volcanic eruptions in what is now Siberia lasted for roughly 1 million years, flooding the atmosphere with carbon and sulfur. Ocean temperatures rose, oxygen in the water plummeted. Around 95% of all marine species went extinct. 70% of land vertebrates disappeared. The fourth came 200 million years ago, at the end of the Triassic, and cleared the way for dinosaurs to dominate. The fifth, 66 million years ago, was the asteroid. It killed the non-avian dinosaurs and opened the door for mammals. Each extinction was a hard reset. Whatever complex chemistry, whatever sophisticated organisms, whatever potential for intelligence had been building up, almost all of it was erased. The survivors started again from a radically simplified gene pool. Here is what most people do not consider. Each reset also erased the record. The upheaval that killed the species also churned the sediment, flooded continents with lava, buried layers under ash, and acidified the ocean until fossils dissolved. The evidence of what existed before each extinction is degraded at the exact moment when the most dramatic things were happening. The periods just before each of the Big Five extinctions are some of the hardest chapters of Earth's history to read, precisely because the ending of those chapters was so violent. So, every time we look at those boundary layers in the rock and try to reconstruct what Earth was like before the catastrophe, we are reading a page that was partially shredded before we got to it. And one of those catastrophes, the Great Dying, left behind anomalies in the rock that scientists are still trying to explain 200 million years later. 252 million years ago, 95% of everything living in the ocean died. Imagine the Pacific Ocean today, with all its creatures, its coral reefs, its schools of fish, its whales and squid, and microscopic plankton. Now imagine almost all of it gone, not reduced, not struggling, gone. That is the Permian-Triassic extinction, the largest mass extinction in the history of complex life on Earth. The cause is mostly understood. Massive volcanic eruptions in what is now Siberia released enormous amounts of carbon into the atmosphere over roughly 1 million years. This is called the Siberian Traps event. The carbon warmed the planet, acidified the oceans, and collapsed the marine food web from the bottom up. But here is what scientists keep finding in the boundary layer, the thin line in the rock where the Permian ends and the Triassic begins. The carbon isotope signature at the extinction boundary shows a sudden, sharp negative spike. This means a large amount of carbon with a specific chemical fingerprint flooded into the system very rapidly, faster than the Siberian traps alone can fully account for. The exact timing and the exact magnitude of that spike are still subjects of active research. Some scientists believe methane hydrates on the seafloor destabilized and released stored carbon in a runaway cascade. Others believe organic-rich sediments were superheated and vaporized by the volcanic intrusions. A few point to an extraterrestrial impact as a triggering mechanism, though evidence for that is thin. What is not debated is the outcome. The biosphere collapsed. The ocean chemistry shifted so radically that most creatures with calcium carbonate shells, nearly every species of coral, brachiopod, and marine invertebrate, were chemically dissolved away. It took roughly 10 million years for ocean ecosystems to approach anything like their previous complexity. 10 million years of recovery. For perspective, that is longer than the entire evolutionary history of our genus. After the Great Dying, the planet that emerged looked completely different. New groups of animals filled the ecological roles left empty. The Triassic world was rebuilt from scratch, using whatever survived, and what survived, and what eventually came to dominate after the next extinction, turned out to have potential that nobody could have predicted from the rubble of the Permian. Something was coming that would run this planet for over 160 million years. 66 million years ago, a rock roughly 6 miles across, traveling at about 45,000 miles per hour, hit what is now Mexico. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously. The rock punched through Earth's crust. The ocean vaporized. Earthquakes shook every continent. Wildfires started across multiple continents within hours as heated debris rained back down through the atmosphere. Then came the winter. Debris and soot blocked sunlight for months, possibly years. Photosynthesis stopped in much of the world. The food chain collapsed from the base up. About 75% of all species went extinct, including all non-avian dinosaurs. The ones that survived were mostly small, creatures that could burrow, that could eat seeds or insects or carrion, that could wait out the darkness. Mammals were among them. Small, warm-blooded, hiding in the debris of the old world. Here is the piece that matters most for our story. The mammals that survived the asteroid impact had existed alongside dinosaurs for over 100 million years. They were mostly nocturnal, mostly tiny, mostly hiding. They had never had the opportunity to dominate large ecological roles because dinosaurs occupied all of them. The asteroid did not create mammal intelligence. It created the opportunity for it by eliminating the competition. Within 10 million years, mammals had diversified into nearly every ecological niche the dinosaurs had vacated. By 50 million years ago, the first primates had appeared. By 6 million years ago, the lineage leading to humans had branched off from our common ancestor with chimpanzees. And by 300 years ago, one branch of that lineage had dug up the compressed remains of ancient organisms, set them on fire, and begun pumping carbon into the atmosphere at a pace that, geologically speaking, is nearly instantaneous. Now here is the question those facts raise. That process, the rise of intelligence, the building of a technological civilization, the rapid carbon release, took only 300 years to reach industrial scale once it started. Our total time as a species is 200,000 years. Our time as a tool-using, fire-using, socially complex creature goes back perhaps 2.5 million years. Compared to the 160 million years dinosaurs had, compared to the 2+ billion years before the oxygen revolution, compared to the 4 billion years before us, the window for intelligence to develop and for civilization to rise and fall is very short. Ours might be typical. And if it is typical, then the question is, how many similar windows have opened on this planet before the record was destroyed? The next chapter goes to a world far away from Earth. And what Webb found there may be the most important clue yet. 124 light-years from Earth, in the constellation Leo, a planet is covered by a global ocean. It is called K2-18b. It is about 8.5 times as massive as Earth, and nearly 3 times larger in diameter. Its star is smaller and cooler than our Sunday. It orbits in the habitable zone, the region where liquid water can exist on a planet's surface. In 2023, the Webb telescope detected something in its atmosphere, and in April of 2025, that detection was strengthened with a second, independent instrument. The chemicals were dimethyl sulfide and dimethyl disulfide. On Earth, these two molecules are produced exclusively by living things, primarily by marine microorganisms, phytoplankton, living in the ocean. There is no known geological or chemical process on Earth that produces them in significant quantities without biology. The concentration detected on K2-18b was thousands of times higher than what we find in Earth's own atmosphere. Scientists were immediately careful, and correctly so. A molecule that is only produced by life on Earth might still be produced by non-biological processes on a completely different type of planet with a different chemistry. The detection needed independent confirmation and more data. In fact, a follow-up analysis published in mid-2025 by a NASA-led team found the signal was less conclusive when all the available data were combined. The debate is ongoing, but the initial finding and the methodology behind it changed something fundamental. For the first time in human history, we aimed a telescope at a planet orbiting another star in the habitable zone and detected chemicals that, here on Earth, only life makes. And those chemicals showed up at concentrations that demand an explanation. The lead researcher at Cambridge, Niku Madhusudhan, said something that will likely be quoted for a long time. He said this might be the tipping point, the moment when the question of whether we are alone in the universe becomes one we are actually capable of answering. And here is where K2-18b connects directly back to Earth's story. Webb proved it can read chemical fingerprints from the atmosphere of a world over 100 light-years away. It can distinguish between molecules. It can detect life chemistry, or at least things that look like life chemistry, from enormous distances. Now turn that mirror around, point it at Earth from 100 light years away, and look, what do we see? Carbon dioxide, rising fast, methane from agriculture, nitrogen oxide from industry. A chemical fingerprint that, to an outside observer, would look like a rapid and unusual biological and industrial perturbation happening on a rocky world in a habitable zone. That is exactly what we would look like from space right now. And that is exactly what a prior civilization on Earth might have looked like for a brief window in time before the geology erased the details. Right now, humans are writing a message into the rock that will last millions of years. Scientists call our era the Anthropocene, the age of humans. It is a formal geological concept. Future geologists, whether human or not, will be able to find this moment in the rock record hundreds of millions of years from now. The markers we are leaving are unmistakable. Radioactive isotopes from nuclear weapons testing in the 1950s and 60s are present in sediment layers around the entire world. Future scientists will find a thin but global spike in plutonium and cesium at exactly this moment in geological time. Microplastics are now found in deep ocean sediment, in Arctic ice cores, in mountain glaciers, in the tissue of marine organisms. Plastic does not biodegrade in geological time. It fragments, but the polymer chains persist. This layer will be readable millions of years from now. Industrial metals, lead, cadmium, mercury, chromium, have spiked in concentrations in ice cores and ocean sediment across the entire planet, starting precisely with the Industrial Revolution. Carbon isotope ratios in the atmosphere have shifted measurably as we burn ancient fossil carbon and dilute the atmospheric record with carbon that has a specific isotopic signature distinct from biological sources. Nitrogen and phosphorus from agricultural runoff have altered ocean chemistry globally. Concrete. Around 30 billion tons of it has been produced by humans. Individual pieces will not survive millions of years, but the chemical signature of processed limestone and silicate will appear as an anomaly in the sedimentary record wherever cities were built. Take all of these markers together and they form a clear, unambiguous, globally synchronous signal. Any future scientist with the right tools would know, without question, that something industrial and biological happened right here at this precise moment in geological time. Now run that forward 100 million years. Subduction has recycled the ocean floor. Erosion has stripped the surface of former continents. Rain and chemical cycling have diluted and scattered the markers. What remains? Possibly a faint carbon isotope anomaly. Possibly some elevated metal concentrations in certain deep water sediment that was not subducted. Possibly isotopic spikes that survived in specific geological formations. Something that, to a future scientist without context, might look like an unusual but not impossible natural event. Might look exactly like what we are seeing in that carbon spike 56 million years ago. The scientists who wrote the Silurian hypothesis were not saying a civilization definitely existed. They were saying that if one did, the record left behind would look like exactly what we are finding, and we would not know the difference. And the planet that created the conditions for all of this has been doing something remarkable for billions of years. Something that has both preserved and destroyed evidence in equal measure. Earth is not a passive museum. It is an active recycling system. The surface we stand on is constantly moving. Continents drift. Mountain ranges rise and erode. Volcanoes erupt and bury landscapes under ash. Glaciers grind forward and retreat. Rivers carry material from highlands to deltas. The seafloor spreads at mid-ocean ridges and sinks back into the mantle at subduction zones. This continuous churn is what makes Earth habitable over billions of years. It regulates carbon. It cycles nutrients. It keeps the chemistry of the atmosphere and ocean in a range that supports life. But it also destroys the record of what came before. The ocean floor is the most active eraser. At subduction zones, oceanic crust dives beneath continental crust and sinks into the mantle, at depths of up to 400 miles. The rock melts. Everything on and in that rock, fossils, sediment layers, chemical traces, is destroyed, recycled into new magma that will eventually erupt as new rock somewhere else on the planet. The entire floor of the ocean is replaced roughly every 200 million years. This means anything that happened primarily in or under the ocean before 200 million years ago is likely gone, physically, chemically, completely. On land, erosion works more slowly, but just as effectively over long timescales. A mountain range that took millions of years to build can be worn completely flat in another 100 million years. The sediment that eroded from it gets carried to the sea, deposited, compressed into new rock on the continental shelf, and eventually subducted. The original mountain is gone, and so is whatever was on it. Even chemical signals in rock decay. Radioactive isotopes transform into daughter products. Organic molecules break down into simpler compounds. Specific mineral signatures get overprinted by later geological processes. Here is the number that captures all of this. Of the 4.5 billion years of Earth's history, we have coherent, detailed rock records from only a fraction of that time. The deeper we go, the sparser the record becomes. Below about 500 million years, it is fragments. Below 2 billion years, it is mostly chemical and isotopic clues. Below 4 billion years, it is almost nothing. We are trying to read a book where most of the pages are missing. Many of the remaining pages are water damaged and torn, and the first few chapters were never printed at all. And in that same geological engine that erases the past, an interstellar visitor arrived recently and brought a message from somewhere else entirely. In the summer of 2025, a comet appeared in the sky. Astronomers spotted it, calculated its orbit, and realized immediately that something was different. Its trajectory was hyperbolic. It was moving too fast and at too steep an angle to have come from within our solar system. This comet, designated 3I Atlas, came from another star system entirely. It was the third interstellar object ever detected passing through our solar system. The Webb Space Telescope turned toward it as it swung around the sun and used its spectrograph to read the chemistry of the coma, the cloud of gas that boils off a comet's surface in the solar heat. What Webb found was fascinating and strange. The chemistry was broadly similar to comets from our own solar system. Water, ice, carbon-based compounds, the kinds of molecules that planetary scientists recognize. But the ratios were different. A slightly higher carbon dioxide to water ratio than typical, more nickel relative to iron than expected, and, crucially, a carbon isotope ratio that was distinctly different from anything found in our solar system's own comets. That carbon isotope signature was the star's fingerprint. The comet formed in a different solar system with a different chemical composition, and it carried that chemistry with it across interstellar space. The researchers at NASA noted something that stopped the conversation. They pointed out that we only know of one place in the universe where chemistry led to life. Our solar system, our Earth. This interstellar object gave them a window into the chemistry of another star system, and they found that the building blocks were present there too, arranged differently, in different ratios, but present. Now consider what this means for the broader story we have been building. Carbon, the molecule life uses as its backbone, forms in space. It travels inside comets. It gets delivered to planets. This is not unique to Earth. It is happening across the galaxy. If another solar system has rocky planets in habitable zones, those planets almost certainly received carbon deliveries from comets just as Earth did. If those planets had liquid water and the right temperature range, chemistry had billions of years to run experiments. And if any of those experiments succeeded, the chemistry that Webb can now detect from over 100 light-years away would show up in that planet's atmosphere as a chemical fingerprint. The interstellar comet 3I Atlas reminded scientists of something they already knew but had not felt this concretely before. the raw material for life is not unique to Earth. It is scattered across the galaxy, moving from star to star inside frozen travelers like this one, which means the question is no longer whether life could exist elsewhere. The question is where to look first. And it turns out, one of the most promising places to look might be the one we have been looking past this entire time. A planet we already live on. A planet that has been running chemical experiments for 4.5 billion years. A planet whose early chapters are gone, whose middle chapters are fragmentary, and whose recent chapters we are only now learning to read. The story of what happened here before us is not closed. The evidence is just buried deeper than anyone thought to look. And what we find when we look at the deepest layers is going to force a question that science has been carefully avoiding. 2/3 of Earth's surface is covered by ocean. Of all that ocean floor, less than a fraction of a percent has ever been directly observed by human eyes or cameras. A study published in 2025 put a precise number on it. Every dive ever made in the deep ocean, every remotely operated vehicle, every camera ever lowered below 650 feet, the total area ever photographed adds up to roughly the size of Rhode Island. Rhode Island, in an ocean that covers more than 129 million square miles. We have more detailed maps of the surface of Mars than we have of our own ocean floor. Now think about what that means for this conversation. If evidence of a prior complex civilization exists somewhere on Earth, and if any part of that civilization operated near water, as ours does, as almost every civilization in human history has, then the most likely place for traces to remain is in deep ocean sediment, quiet, low oxygen, undisturbed sediment layers that accumulated slowly over millions of years and preserved chemical signals that erosion on land would have long since scrubbed away. And we have photographed an area the size of Rhode Island. There are places on the deep ocean floor that have not been disturbed in millions of years. Abyssal plains, vast flat regions at depths of over 3 miles, where sediment accumulates in thin layers year after year, century after century, undisturbed by current or life. These regions act as the most faithful geological archives on the planet. Whatever chemistry settled into them, settled and stayed. Some researchers who take the Silurian hypothesis seriously have pointed to exactly this. If you want to search for anomalous chemical signals that might hint at a prior industrial episode, the deep ocean abyssal plain sediment is the most promising place to look, not because anyone expects to find a city down there, but because the isotopic and elemental fingerprints of industrial chemistry, the kinds of signals our own civilization is already embedding in seafloor sediment right now, might persist in those deep, quiet layers long after every trace on land has been erased. The problem is cost. A single deep ocean research expedition runs into tens of millions of dollars. Coverage is clustered around cable routes and proposed mining sites. The vast majority of the abyssal plain has never been touched. We are essentially telling ourselves there is nothing down there before we have looked. And what might be buried in those layers connects directly to the strangest and most unexplored period in Earth's entire history. Between 1.8 billion and 800 million years ago, Earth got stuck. The planet was warm. The continents were assembled. The oceans were full of single-celled life. The atmosphere had oxygen, but only a fraction of what we breathe today. And then, for roughly 1 billion years, almost nothing changed. No major ice ages, no dramatic carbon swings, no explosion of new complexity. Just a long, warm, chemical stasis that geologists eventually named the boring billion. For 1 billion years, the most sophisticated life on Earth was a single cell with a nucleus. Scientists spent decades trying to understand why evolution stopped. Why did complex multicellular life not emerge for 1 billion years after the oxygen revolution? The answer turned out to be chemistry. The oceans during this period were depleted in the nutrients that drive biological innovation. Molybdenum, iron, nitrogen, phosphorus, all of them locked away by low oxygen chemistry that kept the ocean chemistry stable but unproductive. Without the right nutrients, Complex life could not gain the energy advantage it needed to diversify. The planet was in a kind of holding pattern, geologically stable, biologically waiting, chemically balanced at a point that was almost perfectly self-sustaining. Then, around 800 million years ago, something broke the pattern. The supercontinent Rodinia began splitting apart. New coastlines formed. Shallow seas expanded. Nutrients flooded into the ocean. Oxygen started climbing. And within a few 100 million years, after the double freeze of snowball Earth shook everything loose, the Cambrian explosion happened. The boring billion ended, and complex life surged forward. But here is what does not get discussed enough. A billion years is an enormous amount of time. Our industrial civilization is 300 years old. Our entire species is 200,000 years old. A billion years is 5,000 times longer than the entire time complex life has existed on Earth. During that billion years of relative chemical stability and warm global ocean, something was happening. Single cells were evolving into the first eukaryotes. The first experiments with multicellularity were being run and abandoned. Chemistry was doing what chemistry does in warm, mineral-rich water. With plenty of time, we assume nothing interesting happened because the rock record shows stability. But stability at the macro scale does not mean nothing was happening at the molecular scale. And the molecular scale is where the really important experiments happen. Something built inside that billion years. And when the lid finally came off, what emerged was unlike anything that had come before. And it was not the only time something built quietly in the dark. 350 million years ago, something happened that would power the 20th century, the Carboniferous period. It takes its name from carbon because the forests that grew during this era eventually became coal. Enormous trees covered the lowlands. Not trees like the ones outside your window. These were plants with woody trunks that had only recently evolved lignin, the tough structural material that let plants grow tall. The fungi and bacteria that would eventually learn to decompose lignin had not caught up yet. So when these trees died, they did not rot. They piled up in swamps and bogs, layer on layer, slowly compressed under sediment over millions of years, eventually cooked by heat and pressure into dense black carbon. That carbon is the coal that powered the Industrial Revolution, the oil that runs most of the world's engines, the gas that heats most of its buildings. We are burning the Carboniferous. Atmospheric oxygen during this period peaked at around 35%, compared to the 21% today. That extra oxygen is why insects grew to terrifying sizes during the Carboniferous. Dragonflies with wingspans as wide as a football and centipedes as long as your arm. The air was so rich in oxygen that wildfires burned hotter and spread faster than at any other time in Earth's history. The Silurian hypothesis paper made a specific point about this. By the Carboniferous period, around 350 million years ago, there was already sufficient fossil carbon in the ground to fuel an industrial civilization comparable to our own. The raw materials were already there. Scientists who wrote that paper were not saying anyone used them. They were making a chemical argument. If the preconditions for a fossil fuel civilization include having enough buried carbon to burn, then those preconditions existed on Earth far earlier than we typically consider. The Carboniferous forests lived. They died. They compressed. And 300 million years later, we dug them up and set them on fire. What we are releasing now is chemistry that was locked away before the dinosaurs existed, before mammals existed, before the asteroid that would eventually clear the way for our ancestors had ever left its orbit. We are reaching into deep time and igniting it. And that combustion is leaving exactly the kind of chemical signature in the atmosphere that a prior civilization would have left behind, except ours is larger and faster and more measurable. The question scientists are only beginning to formally ask is whether something similar happened before, at a smaller scale, and whether any trace of it survived. Imagine a crime scene with no body, no weapon, no fingerprints, and no witnesses. The only thing left is a faint smell in the air that might mean something or might not. That is what searching for a prior civilization on Earth actually looks like. The scientists who first formally examined this in 2018 were explicit. They were running a thought experiment. They doubted a prior civilization existed, but they asked whether the geological record could disprove it, and their answer was no. The record cannot disprove it. It lacks the resolution to do so. Here is why the problem is so hard. The thing we are looking for, a brief industrial episode lasting a few hundred years on a geological timescale that is billions of years deep, is almost perfectly designed to be invisible. A sustainable civilization, one that found ways to generate power cleanly and recycle its waste, would leave even less of a mark than an industrial one. The more advanced and less polluting the technology, the smaller the geological fingerprint. A civilization that cracked clean energy and did not strip mine the planet for fossil fuels would leave almost nothing in the rock record. Ironically, our own civilization is detectable precisely because of how destructive it is. Radioactive fallout, plastic pollution, industrial metals, carbon isotope spikes. We are writing our chapter in permanent ink because we are doing it so aggressively. A cleaner civilization might write it in water. There is also the issue of what we even call civilization. We define it by complexity, by technology, by energy use. But life has been doing complex chemistry on this planet for 4 billion years. The ocean runs chemical reactions that rival anything in a laboratory. Microbial ecosystems in the deep sea operate at scales and efficiencies that engineers are still trying to understand. If we are looking for a civilization in our own image, we might miss something that looked completely different, organized, energy-using, self-sustaining, but built on chemistry we would not recognize as technology at all. The planet is 4.5 billion years old. We have been looking seriously for maybe 50 years, and we have barely started checking the right places. The cover of the perfect crime is time, and Earth has had more of it than almost anything else we know. The next planet over knew something about time too, and it ran out. Our solar system has 3 rocky planets in or near the habitable zone. Earth sits in the middle, Mars is outside, Venus is inside. Both of them were once potentially very different from what they are today. Mars shows clear evidence of ancient rivers, valley networks carved into the surface by flowing water, crater lakes with sedimentary rock deposits showing signs of long-term water chemistry, minerals that only form in the presence of liquid water. The Curiosity rover confirmed that Gale Crater held a lake that lasted for potentially millions of years. Somewhere between 3 and 4 billion years ago, Mars had liquid water on its surface, possibly an ocean in its northern hemisphere, a thicker atmosphere, temperatures that allowed liquid chemistry, and then it lost its magnetic field. Without a magnetic field, the solar wind stripped the atmosphere away. Without an atmosphere, the water boiled off into space or froze underground. Mars dried out and froze over, a process that took hundreds of millions of years. What happened to any chemistry that was running during Mars's wet period? Same answer as always, mostly gone. The surface has been bombarded by radiation for billions of years. Without an atmosphere to protect it, the surface chemistry has been obliterated. Whatever was happening in that ancient lake is buried under dust and impact craters and 3 billion years of exposure to unshielded solar radiation. Venus is the other warning. NASA climate models suggest Venus may have had a shallow liquid water ocean and habitable surface temperatures for up to 2 billion years of its early history. 2 billion years is an enormous window, long enough for life to not just start, but to reach extraordinary complexity. Then something happened. Current understanding points to a runaway greenhouse effect. As the sun brightened over billions of years, Venus could not shed heat fast enough. The oceans evaporated. Water vapor is a greenhouse gas. More water vapor made it hotter. More heat evaporated more water. A feedback loop that had no break. Today, Venus has surface temperatures around 870 degrees Fahrenheit. Its atmosphere is thick with carbon dioxide. It crushes anything that lands on it within hours. Our closest neighbor is a cautionary tale about what happens when a planet crosses a climate threshold it cannot come back from. And Earth is currently pushing its own atmosphere toward more carbon dioxide, more heat, and less predictable equilibrium. We are not Venus. Our planet has stabilizing feedbacks Venus lacked. But Mars and Venus together represent two different failure modes. Lose the magnetic field and the atmosphere bleeds away. Trigger a runaway greenhouse and the planet cooks. Both of our neighbors failed. Earth survived, and the question is whether surviving means we are the first intelligent chemistry that ran long enough to ask these questions, or simply the latest in a series of experiments that the planet has been running for a very long time. In the early 1990s, a geologist named James Kennett noticed something strange in deep ocean sediment cores from around 56 million years ago. The carbon isotope ratio dropped sharply. The temperature proxies spiked. It looked like someone had injected a pulse of ancient organic carbon into the atmosphere in a very short period of time. That was the discovery of the Paleocene-Eocene thermal maximum. Since then, scientists have drilled into the sediment record all over the world and confirmed it. The signal is global. The timing is tight. The chemistry is anomalous. The most recent research points toward volcanic activity from the North Atlantic igneous province as the most likely trigger, possibly superheating organic-rich sediments and releasing stored carbon very rapidly. Mercury spikes in sediment cores from North Sea drill sites suggest pulsed volcanic episodes right at the boundary, but the exact mechanism is still debated. The rate of carbon injection, how fast it happened, the precise total amount, these numbers remain uncertain because the record is imprecise at the scale of thousands of years. And here is the detail that matters most for our story. Scientists studying the Paleocene-Eocene event have explicitly noted that the rate of carbon injection was, in some estimates, comparable to what modern human industry produces. This is why researchers studying the event call it the best geological analogy for anthropogenic climate change. The rate was comparable. The effect on ocean chemistry was comparable. The recovery time was enormous. If you were a future scientist, 100 million years from now, analyzing a sediment core that included the boundary where the Paleocene-Eocene event occurred, here is what you would see. A carbon isotope anomaly, a temperature spike in the proxy record, elevated mercury in some cores suggesting volcanic activity, and then a slow recovery over 200,000 years. Now add another layer. You are also analyzing a sediment core that includes our current era. You see another carbon isotope anomaly, smaller in total but faster in rate, alongside elevated microplastics, radioactive isotopes, industrial metal concentrations, and a globally synchronous signal starting in the mid-20th century. The question a future scientist would ask is, are these the same kind of event? The answer, with full context, is probably no. One is industrial, one is geological. But without full context, without knowing which layers to look at carefully and which assumptions to challenge, the two signals rhyme in uncomfortable ways. That rhyme is the heart of the mystery. And what comes next is the tool that might eventually let us tell them apart. In 2025, a team at the SETI Institute ran a simulation. They used the James Webb telescope as a model and asked, if a planet exactly like Earth, orbiting a star exactly like our Sun, was located 30 light-years away, what would Webb be able to see in its atmosphere right now? The answer included nitrogen dioxide, a gas produced by burning fossil fuels and by internal combustion engines. A gas that, on Earth, is more concentrated over cities than over oceans. A gas that has been building in our atmosphere since the Industrial Revolution. Webb can detect nitrogen dioxide in an exoplanet's atmosphere at those concentrations, with enough observing time. The signal is faint at 30 light-years, but it is detectable in principle. That is a techno-signature, not a biosignature, not just life, technology. NASA ran a separate analysis showing that chlorofluorocarbons, the synthetic industrial gases we used in refrigerants before the ozone crisis of the 1980s, would also be detectable around nearby exoplanets. These gases have no natural source. They are produced exclusively by industrial chemistry. Their presence in an atmosphere would be unambiguous evidence of technology. Upcoming telescopes are designed specifically with this in mind. The Habitable Worlds Observatory, planned for the coming decades, is NASA's next flagship telescope. It is specifically built to analyze habitable zone planets in high resolution. Researchers have already modeled what industrial pollution signatures would look like in its data. The Large Interferometer for Exoplanets is a planned European mission targeting the mid-infrared wavelengths, where industrial gases have their strongest fingerprints. These telescopes will let us do something no generation of scientists before us could. We will be able to look at a planet orbiting another star and say, definitively, whether something industrial has been burning fossil fuels there. Now run that capability backward in time. What if Webb had existed 200 million years ago and had looked at Earth? Would it have seen anything unusual in our atmosphere? The answer depends on what was here. If nothing industrial was running, the atmosphere would have looked like what the rock record mostly shows, a planet running on biology, tectonics, and chemistry. But if something had been here, even briefly, even at a scale far smaller than our own civilization, the atmospheric signal would have been there, readable, detectable. We lacked the telescope, and by the time we built one, the signal was already gone. The race now is to build tools powerful enough that when we find an unusual atmosphere around another world, we can finally tell the difference between biology, geology, and something that built things. Right now, under every major city, in the sediment of every river, in the ice cores of every glacier, in the shells of ocean creatures alive today, humans are writing a message. Future scientists, if any exist, will read it, and they will know exactly what happened here, right around the mid-20th century, and what followed. They will find a thin but globally consistent layer of spherical carbon particles from burning coal. They will find elevated concentrations of lead peaking in the 1960s when leaded gasoline was in widespread use, then declining as it was phased out. They will find plutonium and cesium from atmospheric nuclear weapons testing, a spike that appears simultaneously in sediment layers around the entire planet. They will find a global rise in microplastic particles beginning in the 1950s and accelerating each decade since. They will find carbon dioxide concentrations in the atmosphere recorded in ancient air bubbles trapped in ice cores, climbing steeply from about 280 parts per million before the Industrial Revolution to over 400 parts per million within 2 centuries. And they will find the carbon isotope ratio of the atmosphere shifting because fossil carbon has a specific isotopic signature that is diluting the atmospheric carbon pool. This is called the Suez effect, and it is measurable in every organism that breathes air and incorporates carbon into its body. Together, these signals are so clear and so globally synchronous that geologists have formally proposed a new epoch in geological time, the Anthropocene, the age of humans, a boundary as sharp in the rock as the layer of iridium that marks the asteroid impact that killed the dinosaurs. We are leaving a geological scar that will be readable in 200 million years. Here is the piece that quietly terrifies some researchers. The permanence of the signal depends on how long our civilization continues. If humans persist for another 10 million years and keep advancing, the Anthropocene boundary will be rich and deep and unmistakable. If our industrial civilization ends in the next 1,000 years, what remains in the rock will be a relatively brief chemical anomaly in a specific sediment layer. A brief chemical anomaly in a specific sediment layer that future scientists might describe as an unusual but not impossible natural event if they do not know what they are looking at. 56 million years ago, someone, or something, or some geological process left exactly that kind of anomaly, and we still argue about what caused it. Here is a test that scientists have actually run Take all the geological and chemical knowledge we have of the Paleocene-Eocene thermal maximum, the carbon spike 56 million years ago. Strip away the knowledge that a prior civilization might have caused it. Assume it was natural. Now try to distinguish it, using only the rock record, from the kind of signal our own industrial civilization would leave after another 50 million years of erosion and geological cycling. The conclusion, laid out clearly in the Silurian hypothesis paper, is that you cannot reliably make the distinction. The two signals look similar. The resolution of the geological record at that timescale is not fine enough to tell a fast natural carbon injection from a brief industrial one. This is not a fringe claim. It is a methodology argument. The scientists making it were not claiming a civilization existed. They were pointing out that our geological tools have a resolution limit, and that limit is relevant when we make confident claims about what has and has not happened in Earth's deep past. If we cannot confidently identify our own civilization's signature in the rock record 50 million years from now, how confident should we be that no prior civilization existed? The honest answer is, not very. This does not mean one did exist. The prior probability is still low. Intelligent tool-using life took 4 billion years to appear on this planet once, and there is nothing in the fossil record suggesting anything comparable came before. The strongest argument against a prior civilization is simply that evolution appears to have taken a very long path to get here. But the absence in the fossil record means very little by itself, because brains do not fossilize, cities do not fossilize, and the geological record actively destroys evidence at the same rate that events create it. We are reasoning about a question that our tools are not yet sensitive enough to answer, and that is a different situation from having answered it. The galaxy has been running this experiment on billions of planets for billions of years. And what the galaxy looks like from a distance, how many signals it contains, how many anomalous chemistry signatures sit in the atmospheres of distant worlds, is something Webb is beginning to tell us for the first time. In 1950, a physicist named Enrico Fermi sat down to lunch with some colleagues in Los Alamos, New Mexico. They had been talking about the possibility of extraterrestrial civilizations. The galaxy is enormous. It contains somewhere between 100 and 400 billion stars. Many of those stars have planets. The universe is 13.7 billion years old. There has been plenty of time for civilizations to arise and spread. And then Fermi asked a simple question. Where is everybody? If intelligent civilizations are common, and if even one of them had developed interstellar travel a few million years before us, they would have had enough time to colonize the entire galaxy, multiple times over. We should see signs of them. We do not. The universe appears silent. This became known as the Fermi paradox, and one of the most compelling solutions is called the Great Filter. The Great Filter is the idea that somewhere on the path from simple chemistry to galaxy-spanning civilization, there is a barrier so difficult to cross that almost nothing makes it through. Something kills civilizations, or prevents them from arising, or causes them to collapse before they can expand. The filter might be behind us. Maybe the emergence of complex eukaryotic cells was so unlikely that it almost never happens. Maybe the jump from single-cell life to multicellular animals is a 1 in a billion planets event, and we got lucky. Or the filter might be ahead of us. Maybe every civilization that reaches the industrial stage overheats its planet, or accidentally releases a technology it cannot control, or exhausts its resources before it can build the infrastructure to escape its homeworld. Now add the Silurian hypothesis to this calculation. If the filter is something that civilizations tend to do to themselves, then Earth itself might be a planet where the filter has already operated once or several times. A brief industrial episode, a rapid climate shift, a collapse back to simpler biology, the geological record resets, and a billion years later, a new lineage climbs back up to complexity. The galaxy might be full of planets like Earth, places where chemistry reaches intelligence periodically and then collapses, leaving nothing but a faint chemical smear in the rock. The silence of the galaxy and the silences in Earth's own geological record might be telling the same story. Some scientists are not waiting for better philosophy. They are already looking. The tools of the Silurian hypothesis require examining the geological record specifically for anomalies that match the expected fingerprint of a prior industrial civilization. Not just any anomaly, specific ones. A rapid carbon isotope excursion, elevated concentrations of unusual metals in a specific sediment layer, a globally synchronous chemical signal in a narrow time window, possibly the persistence of certain synthetic-like molecular structures that would not arise naturally. The PETM, 56 million years ago, remains the most discussed candidate, not because anyone believes it was caused by industry, but because its properties overlap enough with what a prior industrial episode would look like that it serves as a useful calibration target. If scientists can fully explain the PETM through natural causes with enough precision to rule out an industrial contribution, that closes a door. If the explanation remains partially open, the door stays ajar. Beyond the PETM, researchers have started looking at other rapid carbon anomalies scattered through the geological record. There have been dozens of smaller carbon excursions over the past several 100 million years. Most are clearly explained by volcanism, orbital changes, or biological events. A few have explanations that are less tidy. None of them have been definitively linked to a prior civilization. There is no smoking gun. The scientific consensus remains that life, geology, and orbital mechanics account for everything in the record we can examine. But the examination is being done now more carefully than it was before the Silurian hypothesis formalized the question. Scientists are asking what they would see versus what they have seen, and checking whether the gap is as wide as assumed. That is how science actually works. Someone formalizes an uncomfortable question, others run the tests. The tests either close the question or deepen it. The test for this particular question is running right now. And every time Webb turns its mirror toward another planet and reads its chemistry, it adds to the toolkit that will eventually let scientists make those comparisons with the precision the question requires. We have reached the point in this story where the threads come together. Earth is 4.5 billion years old. For most of that time, it has been running chemistry experiments, erasing evidence, resetting conditions, and allowing new configurations to emerge. 5 major extinction events wiped the biological slate clean. 2 snowball Earth events physically destroyed vast portions of the geological record. Plate tectonics has recycled the ocean floor multiple times. The Great Oxidation event chemically transformed the sediment and water chemistry of the early world. Out of all of that, somehow, a lineage of bipedal mammals built tools, then language, then science, then a telescope that can read the chemistry of planets over 100 light-years away. And then it turned that telescope around and started asking what it might find in its own planet's past. The James Webb Space Telescope is fundamentally a planet-reading machine. It reads atmospheres, it reads chemistry, it reads the fingerprints that biology and geology leave in the light that escapes from a planet's surface and air. When Webb detected a possible biosignature around K2, 18b, 124 light-years away, it was not just finding evidence of possible life elsewhere, it was demonstrating that a tool exists that can, in principle, detect life chemistry across interstellar distances. When Webb found an unexpected atmosphere around the ancient lava world TOI 561b, twice Earth's mass, orbiting a star twice as old as our Sun, it did not just break a planetary science model. It demonstrated that planets can sustain atmospheric chemistry far longer than our models predicted. It stretched the window of possibility for what has happened on rocky worlds across billions of years. Together, these discoveries do something important for the question we have been circling throughout this entire journey. They expand the parameter space of what is plausible. A planet that can hold an atmosphere for 10 billion years under brutal conditions has a longer window for chemistry to run experiments than we previously assumed. A tool that can read biosignatures from 100 light-years away can, in principle, eventually detect technosignatures as well. A galaxy where the building blocks of life arrive in interstellar comets is a galaxy where the raw materials for complex chemistry are distributed widely. All of this makes the question of what has happened on Earth, specifically, harder to dismiss and more important to actually investigate. The planet is learning to read its own autobiography, and the autobiography is much longer and stranger than anyone thought when we started. The most profound question in all of this is not whether a prior civilization existed on Earth. That question is fascinating and strange and worth investigating, but it is not the deepest one. The deepest question is what it means if one did, and what it means if none did. If a prior civilization existed on Earth and collapsed, leaving only a chemical whisper in the rock, then the story of intelligence on this planet is not a story of inevitable progress. It is a story of rises and falls, of chemistry building up to complexity and then tipping over, of the same planetary stage hosting multiple productions that ended before the audience arrived. That story changes how we think about ourselves right now. We are not the endpoint of a 4 billion year project. We might be the latest attempt, and the question of whether this attempt ends like the others, or whether we find a way to persist long enough to leave something more durable than a carbon isotope anomaly, becomes the central question of our civilization. On the other hand, if no prior civilization existed, if we really are the first complex chemistry on Earth to reach this level of organization, then we are something genuinely rare, and the silence of the galaxy, the absence of detectable signals from other civilizations, becomes even more important. Either we are rare, which means intelligence is harder to achieve than we thought, or we are not rare, which means civilizations tend to be brief, which is its own kind of frightening. Neither answer is comfortable. Both answers have implications for how we treat this planet, this atmosphere, this brief window of complex chemistry that we currently inhabit. The universe has been running experiments for 13.7 billion years, on billions of planets, with 4 billion years of chemistry behind us and some number of years ahead. Whether or not something was here before us, something is here now. And it is the first thing on Earth with the tools to actually ask the question in a way that might eventually have an answer. Our industrial civilization is 300 years old, 300 years out of 4.5 billion. If you compressed Earth's history into 1 calendar year, our industrial era takes up less than 2 seconds. And in those 2 seconds, we have dug up a significant fraction of the compressed carbon that the Carboniferous forests buried over 60 million years. We have altered the chemistry of the atmosphere measurably. We have pushed species extinction rates to levels that, in the geological record, will appear as a 6th mass extinction event. We have planted our chemical and isotopic signature in sediment, ice, ocean, and rock on every continent and in every ocean basin. We have made ourselves detectable, 2 seconds on the planetary calendar. Here is what makes this worth sitting with. A civilization that lasts only 2 seconds on that calendar would leave a faint mark. A civilization that lasts 10 seconds might leave a mark twice as clear. A civilization that lasts a minute starts to become unmistakable. We are in the 2-second window right now, and everything we do in the next 100 years, the next 1,000, the next 10,000, will determine how readable our chapter becomes. Webb demonstrated something critical for this calculation. It showed that the technology to read another planet's chemical history is now within human reach. It showed that biosignatures and potentially technosignatures can be detected from light years away. It showed that the atmospheric record of a world persists long enough to be read, which means that what we are writing into Earth's atmosphere right now is being written for an audience that may arrive in the future, or from far away, or both. The Carboniferous period left coal, the mass extinction events left boundary layers, the PETM left a carbon anomaly. We are leaving radioactive isotopes, plastics, industrial metals, a steep carbon curve. The question is whether we also leave something else. a civilization that figured out how to stabilize itself before the window closed. A story that keeps going past the 2-second mark, because the universe, as far as we can tell, has been waiting a long time for something complex enough to ask that question. Here is what the James Webb Space Telescope has shown us in its first few years of operation, taken together as a single picture. It found ancient galaxies that formed far too quickly after the Big Bang, suggesting our models of early universe structure need revision. It found carbon clouds forming in the universe's first few 100 million years, pushing back the window for when life-essential chemistry was possible. It found that an ancient rocky planet, twice Earth's mass, orbiting a star twice as old as our Sun, retained a substantial atmosphere through 10 billion years of bombardment. It found that our models of which planets can hold on to their chemistry needed updating. It found potential biosignature chemicals around an ocean world 124 light-years away, and triggered a scientific debate that is still running. It found that the tools to detect life chemistry from interstellar distances are now real and operational, not theoretical. It found interstellar comet 3I, Atlas, carrying chemistry from another star system, and confirmed that the molecular building blocks of life travel between stars inside these frozen travelers. It found carbon isotope ratios that are measurably different from anything in our own solar system, proving that other star systems have their own distinct chemical fingerprints. Taken together, these discoveries form a picture. The universe is older than we thought, in terms of when complex chemistry became possible. Rocky planets persist longer than we thought, in terms of how long they hold onto the conditions for complex chemistry. Life chemistry is detectable from interstellar distances, and the raw materials for life are distributed through the galaxy, not locked to any one special location. Earth sits inside all of this. It is a 4.5 billion-year-old rocky planet. It retained an atmosphere. It developed complex chemistry. It ran 5 major extinction events and multiple snowball phases and came back each time with something more complex than before. And right now, a species on this planet has built a machine that can read the history of worlds 100 light-years away with enough precision to detect life and industry. That machine is turning its attention to the question of what we cannot see in our own past. What might have built here before us? What our own chemistry looks like from the outside? And what we are doing to the atmosphere that will one day be someone else's evidence? The telescope is not just a window to the universe. It is a mirror pointed at the deepest questions about what Earth is and what has happened on it. 4.5 billion years of chemistry, 5 mass extinctions, 2 snowball phases, a billion-year pause, an explosion of complex life, a lineage of reptiles that almost crossed the intelligence threshold, an asteroid that reset the board, 66 million years of mammal evolution, 6 million years of primate evolution, 200,000 years of our species, 300 years of industry, and 1 telescope. We are the first thing on this planet that is complex enough to ask whether something complex was here before us. We are the first chemistry that built a machine capable of detecting the signatures of other chemistries on distant worlds. We are the first species with the geology, the spectroscopy, the isotope analysis, and the conceptual framework to even pose the Silurian hypothesis in a rigorous scientific way. That is not a small thing. Whether or not a prior civilization existed on Earth, the question we are asking now is one that has never been asked before, and the tools we are building to answer it, Webb, its successors, the Habitable Worlds Observatory, the Large Interferometer for Exoplanets, are tools that will eventually give real answers to the deepest questions about life's history in the universe. We may find that we are alone, that the 4 billion years it took for intelligence to emerge on Earth is typical, and that the universe is so vast and complex, chemistry so rare, that we are among the very first to get here. We may find that we are not alone, that other planets carry biosignatures, that some carry techno-signatures, that the galaxy has hosted rises and falls of complex chemistry across its entire history, and that Earth itself has hosted more than one. We may find something no one has thought of yet. The universe has a history of doing that. What we know, with the kind of certainty that 4.5 billion years of geological evidence and 3 years of Webb data can provide, is this. The planet is older than our story. The window of possibility is longer than we modeled. The chemistry is more distributed than we assumed, and the tools to read it are, for the first time in the history of this world, in our hands. 56 million years ago, something happened to the atmosphere of this planet that left a mark in the rock and remains only partially explained. Webb just showed us that the mark's chemistry leaves can be read from 100 light years away. The mystery of what came before us is not closed. And for the first time, we have instruments sensitive enough to start taking it seriously. The universe has been waiting for something on Earth to build those instruments. We just did.